Dear students, in this lecture we will discuss Theorem 7.10. So this theorem has three parts. First part, let X be a normed space over K and A be a non-zero element in X. Then there is some bounded linear functional f such that f of A equal to norm A and norm f equal to 1. Consequently, norm A equal to supremum of the set of all mod f of A such that f belongs to x dash and norm f less than or equal to 1. Now next B part. Let Y be a subspace of X and A belongs to X but A does not belongs to closure of Y. Then there is some f belongs to x dash such that restriction of f to y equal to 0, f of A equal to distance of A from closure of y and norm f equal to 1. Also, x belongs to closure of y if and only if x belongs to x and f of x is equal to 0 whenever f belongs to x dash and restriction of f to y equal to 0. And the last part, let set a1, a2, etc. am be a linear independent set in X. Then there are f1, f2, etc. fm in X dash such that fj of ai equal to delta ij where ij varies from 1 to m. Okay, so first we will prove a part, that is X be a normed space over K and A is a non-zero element in X. Then there is some f belongs to x dash such that f of A equal to norm A and norm f equal to 1. Also norm A equal to supremum of the set mod f of A such that f belongs to x dash and norm f less than or equal to 1. Okay, so proof of A part. Here given that A is a non-zero element in X. Okay, now let Y equal to set of all Ka such that K belongs to K. So we have taken Y as like this. Okay, then surely Y is a subspace of X. We can easily show that this set Y is a subspace of X. Now we define a function g from y to k by g of ka equal to k into norm A. This is for all ka belongs to y. Okay. Now clearly g is linear. Here also we can easily show that this map is a linear map. Okay. Now modulus of g of ka, okay, which is equal to modulus of k into norm A. Now if we take k outside from this mode, we have a mod k into norm A. Okay, now by the property of norm we can write this as norm ka. So we have modulus g of ka equal to norm ka. Okay, now modulus g of ka equal to norm ka means this is equal to 1 into norm ka. This is for all ka belongs to y. Okay, so this shows that g is continuous. Okay, here we have take alpha equal to 1. Then we have the condition of continuity. So g is continuous. Okay, and also norm g less than or equal to 1 by the definition of norm g. What is norm g? Norm g is the supremum of the set of all mod g of ka such that ka belongs to y and norm ka less than or equal to 1. So by using that definition we can write norm g less than or equal to 1. Okay, also modulus of g of a by norm A. Okay, we take a by norm A from ka. We have 1 by norm A belongs to k, so a by norm A. Okay, this is equal to 1 by norm A into mod g of A. Okay, or this is equal to, we have mod g of a equal to norm a, so this is equal to 1. Okay, or we can write this as g of a by norm a means we substitute 1 by norm a equal to k. Okay, so this is in the form ka, g of ka. We have seen that modulus g of ka equal to norm ka. Okay, so what is norm k? Norm k means norm of this is equal to 1. Okay, so that means modulus g of a by norm a equal to 1. So from this we can write norm g greater than or equal to 1. Okay, here we have taken this a by norm a from y in a particular case. Okay, a by norm a is a particular element in y. Okay, then modulus of that element equal to 1. Then the supremum. So this is a this may be an upper bound. Okay, otherwise there will be an upper bound. Okay, which is greater than or equal to 1. So we have if we take the supremum, then norm g greater than or equal to 1. This is equation number 2. Okay, so from equation number 1 means norm g less than or equal to 1, and from 1 and 2 we have norm g equal to 1. Okay, now since g belongs to y dash, so here we have shown that g is a continuous linear functional, okay, which is also bounded. So this means g belongs to y dash. Then by Hand-Banach extension theorem, there exists some f belongs to x dash such that restriction of f to y equal to g and norm f equal to norm g. Okay, y is a subspace of x. Okay, now if we restrict this f to this subspace, then the value of that is equal to g. We have defined what is g. Okay, so this means f of a equal to g of a, since a belongs to y. Okay, this is equal to g of 1 into a. That means 1 into norm a, that is equal to norm a. So we have f of a equal to norm a, and also we have by this condition norm f equal to norm g and norm g equal to 1. So norm f equal to norm g, this is also equal to 1. Okay, so we have shown that there is some f belongs to x dash such that f of a equal to norm a and norm f equal to 1. Okay, now we want to show that norm a equal to supremum of this set mod f of a such that f belongs to x dash with norm f less than or equal to 1. Okay, now since f belongs to x dash and a belongs to x, so we have modulus f of a less than or equal to norm f into norm a. Okay, then we have modulus f of a which is less than or equal to 1 into norm a for all f belongs to x dash with norm f less than or equal to 1. If we take norm f less than or equal to 1, then we have this. Okay, then supremum of this set of all modulus f of a such that f belongs to x dash with norm f less than or equal to 1 should be less than or equal to norm a. Okay, since we have this, so this is equation number 3. Okay, also we have just proved that there exists some f belongs to x dash with f of a equal to norm a and norm f equal to 1. Okay, that is norm a belongs to this set, that is set of all mod f of a such that f belongs to x dash and norm f less than or equal to 1. Since we have this f of a equal to norm a, and if we take modulus f of a, this is equal to norm A. So, and also here norm F equal to 1. So these two conditions are satisfied. So that means norm A belongs to this set. So if we take the supremum, then norm A less than or equal to supremum of this set. So from 3 and 4 we have norm A equal to supremum of the set modulus of f of A such that f belongs to x dash with the norm f less than or equal to 1. Okay, so this completes the proof of part A. Next, B part of theorem 7.10. Let Y be a subspace of X and A belongs to X but A does not belongs to closure of Y. Then there is some F belongs to X dash such that restriction of F to Y equal to 0, F of A equal to distance of A from closure of Y and norm F equal to 1. Consequently, X belongs to closure of Y if and only if X belongs to X and f of X equal to 0 whenever F belongs to X dash and restriction of F to Y equal to 0. Okay, so given Y be a subspace of the normed space X, okay, and A be an element in X and A does not belongs to closure of Y, then first we want to show that there is some linear functional f such that restriction of f to y equal to 0, f of a equal to distance of a from y bar and norm f equal to 1. Okay, so the proof of B part. Since closure of y is a closed subspace of X, we know that, okay, closure of y is a closed subspace of X. Now consider the quotient space X by y bar. Okay, now given that A does not belongs to closure of Y, okay, so we have A plus closure of Y is not equal to Y bar. Okay, that means the coset A plus Y bar is not 0 in this quotient space X by Y bar. Okay, that is A plus Y bar is a non-zero element in the quotient space X by Y bar. Okay, so we have this is a non-zero element. Okay, then by part A there is some f tilde from X by Y bar dash such that f tilde of A plus closure of Y equal to the quotient norm A plus Y bar. Okay, and norm f tilde equal to 1. So here we use part 1 of this theorem. Okay, so there is a f tilde from X by Y bar dash satisfying these conditions. Okay, now define f from x to k by f of x is equal to f tilde of x plus y bar. This is for all x belongs to x. So clearly f is linear and also mod f of x which is equal to by definition mod of this, that is mod of f tilde of x plus y bar. Okay, so which is less than or equal to norm f tilde into quotient norm x plus y bar. Since this x plus y bar is an element of this quotient space x by y bar and we take the norm on this as quotient norm, so we have triple norm x plus y bar here. Okay, so which is equal to in norm f tilde into infimum of, we use the definition of this quotient norm, so infimum of the set norm x plus y such that y belongs to y bar. Okay, so which is less than or equal to norm f tilde into x plus 0. Since 0 belongs to, we take in a particular element from y bar, so 0 belongs to y bar. So we have this, and this implies mod f of x which is less than or equal to norm f tilde into norm x. Okay, so this means f belongs to x dash and norm f less than or equal to norm f tilde. This is our equation number 3. Okay, here we have taken our norm f tilde as alpha. Okay, now we show that restriction of f to y equal to 0. So we take an element from y, let y belongs to y, then f of y equal to, by definition, f tilde of y plus y bar. Okay, so this is equal to f tilde of y bar. Since we have y belongs to y, so this implies y belongs to closure of y. Okay, so this is equal to 0, since y bar is the 0 vector of x by y bar and f tilde is linear functional. Okay, so that means f of y equal to 0 for all y belongs to y. So this means restriction of f to y equal to 0. Okay, now we show that f of a equal to distance of a from closure of y. So we have f of a equal to, by definition, f tilde of a plus y bar. So this is equal to quotient of a plus y bar. This is equation by equation number 1. Okay, so this is equal to, by definition of quotient norm, we have infimum of the set of all norm a plus y such that y belongs to y bar. Okay, so this means infimum of the set norm a minus y, both are same. Okay, such that y belongs to y bar. So what is this? This is the definition of distance of a from y bar. So this means f of a equal to distance of a from y bar. Next we want to prove norm f equal to 1. So for this, first we will show norm f tilde which is less than or equal to norm f. So let x belongs to x, then mod f tilde of x plus y bar which is equal to mod f tilde of x plus y bar. Here y belongs to y bar. Okay, so this is equal to mod of f of x plus y by definition of f. Okay, we can write like this. So which is less than or equal to, we split this mod, then norm f into norm x plus y for all y belongs to y bar. Okay, then mod f tilde of x plus y bar which is less than or equal to norm f into infimum of the set norm x plus y such that y belongs to y bar. Okay, so which is equal to, this is the definition of our quotient norm. So which is equal to norm f into triple norm x plus y bar. Okay, so that means norm f tilde which is less than or equal to norm f. So this is our equation number 4. So from 2, 3 and 4 we get norm f equal to norm f tilde which is equal to 1. Okay, so that means norm f equal to 1. So this completes the proof. Next we want to show that x belongs to y bar if and only if x belongs to x and f of x is equal to 0 whenever f belongs to x dash and restriction of f to y equal to 0. So first we let x belongs to y bar, that is closure of y. So then clearly x belongs to x. Okay, now let f belongs to x dash is such that restriction of f to y equal to 0. Okay, now since x belongs to y bar, okay, then we can find a sequence xn in y such that xn converges to x. Okay, and since f belongs to x dash, and xn converges to x, we have f of xn converges to f of x. Okay, that is f of x is equal to limit n tending to infinity f of xn. So this is equal to 0 since the restriction of f to y equal to 0 and xn belongs to y. Okay, so f of xn equal to 0, this is for all n, so that's why this is equal to 0. Okay, so we have assumed that x belongs to y bar, then we have x belongs to x, and here x belongs to x, and f of x is equal to 0. Now conversely, assume that x belongs to x and f of x is equal to 0 whenever f belongs to x dash and restriction of f to y equal to 0. And we have to show that x belongs to closure of y. Let us take the contrary, that x does not belongs to y bar. Then by part B of our theorem, there exists f belongs to x dash such that restriction of f to y equal to 0 and f of x is equal to distance of x from y bar. Okay, this is by first part of B. So that is, we have distance of x from y bar which is equal to 0 since f of x is equal to 0. This is our assumption. Okay, so this is equal to 0. So this means x belongs, the distance of x from y bar equal to 0 means x belongs to closure of y, which is a contradiction to x does not belongs to y bar. So this means we have assumed here x does not belongs to y bar and we have arrived here a contradiction. So that means this assumption is wrong. That means x belongs to y bar. Okay, now C part of theorem 7.10. Let set a1, a2, etc. am be linearly independent set in X. Then there are f1, f2, etc. fm in X dash such that fj of ai equal to delta ij, where I and j varies from 1 to m. Okay, so proof of C part. Let yj equal to span of the set a1, a2, etc. aj minus 1, aj plus 1, etc. am. Here we notice that aj does not belongs to ij. You should note that here aj does not belongs to this set. Okay, then yj is a finite dimensional subspace of X, and hence by theorem 5.4b yj is closed in X. Okay, also we have just mentioned that aj does not belongs to yj, so that means it does not belongs to yj bar also. So aj does not belongs to yj, that is yj means yj bar, that since yj is closed. Okay, so we have aj does not belongs to yj bar. Okay, then by B part of our theorem, there exists some gj belongs to x dash such that restriction of gj to ij equal to 0 and gj of aj equal to distance of aj from yj bar. Okay, now let fj equal to gj divided by distance of aj from yj bar. Okay, then clearly fj belongs to x dash since fj is a constant multiple of g. Okay, gj belongs to x dash, so this means fj also belongs to x dash, and also restriction of fj to ij equal to 0 since this restriction, that is restriction of gj to ij, is also 0. Okay, so we have these two conditions, that is fj belongs to x dash and a restriction of fj to ij equal to 0. Okay, also fj of ai, which is equal to gj of ai divided by distance of aj from yj bar. This is equal to 0 if I not equal to j. Since if I not equal to j, okay, then ai belongs to our yj bar. Okay, then gj of ai equal to 0. So for this case, this is equal to 0. Now if I equal to j, then what will happen? Fj of aj, that is equal to, by definition, gj of aj divided by distance of aj from yj bar. Okay, we have gj of aj is distance of aj from yj bar. This already we have. Okay, so this means fj of aj equal to 1. This is when I equal to j. Okay, that is fj of ai equal to delta ij, that is equal to 1 if I equal to j, or 0 if I not equal to j. Okay, so this completes the proof of theorem 7.10. Okay, thank you.